Are you getting sound from me? Is the little meter going? Okay. All right, so this is lecture 3. We're covering section 6.2. Section 6.2 is titled Trigonometric Integrals and Trigonometric Substitutions. So today we're discussing trigonometric integrals. And those are simply integrals that have whose integrands are made up of trig functions. On Monday, we'll do part 2 of this topic, and we'll discuss trigonometric substitutions. That will deal with integrals whose integrands don't have trig functions in them, but after you make a substitution, it turns out they do, and then you come back and you apply the techniques that we're learning today. All right, part 1 is integrals where we do a basic thing, which is to break off a sine or cosine, a single one, and then do substitution. Now I mentioned, well, you know, on the web page, I mentioned in the descriptions of the quizzes and exams, there's always at least one problem that's based very closely on a book example. So the quiz you have today has a problem based on a quiz example, actually 2. And that's to encourage you to read the book and read its examples, because A, the book is really good, and B, I'm not going to cover stuff in lecture if it's covered well in the book, or generally. So I actually make a list of all the topics, and if something's covered well in the book, I often don't cover it in lecture. Sometimes I do, but I want there to be some problems where I have not talked about them in lecture. You had to learn about them by working on your homework. It's Elon. He's such a pest. All right, so this one thing nice about this section of the book is they have descriptions like this of a few different techniques, and it's very helpful. There are 3 or 4 different approaches that are taken in this section of the book, and they don't word them quite with this many words, but this is the first one they discuss as well. Oh my gosh, it's Elon. All right. Because I'm an important dude, Marcy. All right, so let's do example 1. Find this integral. Well, the trick here is to break off one of the factors of cosine. And then we're going to use a trig property. Cos squared x is 1 minus sine squared x. Then we can distribute this. This gets distributed there and there, so I end up with the integral of sine to the 11th of x, which I hate that notation. That should be sine of x in parentheses raised to the 11th power. But I didn't make up this notation. And then sine to the 13th of x. And then all of this is multiplied by cos x. Okay, now this brings us to the second thing that I mentioned was, you break off a sine or a cosine. Now let's write this a different way. This is actually better written as sine of x raised to the 11th minus sine of x raised to the 13. That's the notation that I really prefer, to be honest and clear about the order of operations. So there we go. So you see, this is a pain because it's a nested integrand. We would really rather not have that inner function. So we do substitution details. We, first of all, figure out a new version of that sine x. That's our inner function. We're going to call that u. So that's going to be our green substitution. And then we always do the same thing. Well, I always do the same thing. I find a new version of that dx. Dx is 1 over u prime du, so 1 over cos x du. So that's going to be our red substitution. So when I do that, I get u to the 11th minus u to the 13, and I still have cos x, but then I have 1 over cos x du. So I did that red substitution there, and I did that green substitution there. So this is, and then notice that's the substitution step, and then I cancel. So I end up with the integral of u to the 11th minus u to the 13. Now remember from Calc 1, I'm a stickler for notation. The point of the substitution method is that you do a substitution and you end up with a new integral that's a clean integral involving just u, or whatever variable you've chosen. And there should not be any x's in there. And there should be a du. I want to see all those things in the details of your work. And the reason is, for one thing, your math writing should just be clear, but also we found in Calc 1 that there are some problems where a substitution method doesn't work. There's like a nested function, and it turns out that you embark on substitution, and at some point you run aground, and where you run aground is this step. You can't get to a place where you just have a clean integral involving u. So you want to make sure that you make your notation clear so that when something comes up that's wrong, it's glaring, because then stuff is not, stuff looks weird on the paper. So the result of the substitution step should be a clean integral involving just u. So then this is going to be u to the 11 plus 1 over 11 plus 1 minus u to the 13 plus 1 over 13 plus 1. So that's u to the 12th over 12 minus u to the 14th over 14 plus c. Then I substitute back. That's sine x to the 12th over 12 minus cos x to the minus sine x to the 14 over 14 plus c. WebAssign will accept this notation. It will also accept sine raised to the 12th power of x, that evil notation. All right. Part 2, I'm going to put over here. Useful trig formulas. So we've already used one, sine squared x plus cos squared x equals 1. That's the Pythagorean theorem. And then we have double angle formulas, like this one. So out of the deep recesses of your brain, recall this, that sine of A plus B is equal to sine A cos cos B minus plus sine cos A sine B. So if I replace B with A, sine of A plus A, that's going to be sine A cos A plus cos A sine A. Well, those two terms are identical. They're just written in opposite order. So this is 2 sine A. On the left side, this is sine 2A. Oh, this is not right.
2 sine A cos A.
Yeah, 2 sine A cos A. So that's one useful trig formula. All of these are useful, but I'm going to circle this one. Of course, there's another version of this where you could divide both sides by 2, but I'm not going to bother with that. Now, there's another double angle formula, which is cos A plus B. And remember that that's cos A cos B minus sine A sine B. So if I replace replace B with A, I get cos of A plus A equaling cos A cos A minus sine A sine A. So on the left I have cos 2A. And on the right I have cos squared A minus sine squared A. So that's actually a useful formula. But again, they're all useful. I'm not going to circle all of them. But here we can go a couple of different ways. And I am going to go these two ways. One is to get rid of this sine squared. Remember, sine squared is 1 minus cos squared. So I can do that, and notice that I end up with minus a minus cos. I get 2 cos squared A, and then a minus 1. So, this would be useful going either direction. If you got one of these, you can replace it with one of these. Now I'm going to rewrite this. I'm going to add 1 to both sides, and I'm going to then divide by 2, and I get this. Cos squared A equals 1 plus cos 2A all over 2. Now that one is going to often be useful. So all of these things are called double angle formulas because they're an equation where in one of the terms you have an angle that's written a double some particular angle. Now let's go another route. Let's take this and let's get rid of the cos squared. So cos of 2A equals 1 minus sine squared A, and then minus sine squared A. Okay, so then I end up with 1 minus 2 sine squared A. Now I'm going to describe verbally what I'm going to do, but I'm not going to write down all the steps. If you want to see this, you can go back and watch the video. I'm going to subtract 1 from both sides, so I'll have cos 2A minus 1 equaling minus sine squared A. And then I'm going to divide by minus 2, and that's going to reverse the order of the terms on the left side. So I'm going to end up with 1 minus cos 2a over 2 equals sine squared a. So again, this is just algebra. You can, if you're confused about this, work on it on Martin Luther King Day. All right, that's part 2. Part 3 is integrals involving double angle formulas. So here's one. Example 2 is this definite integral. Integral from 0 to pi over 8 of sine squared x cos squared x. Now there's more than one way to do this. Now I'm going to call this SA for signed area. And let's right away use the fundamental theorem of calculus to make sure that we know what we're going to, our approach. We're going to find the indefinite integral of sine squared x cos squared x. And then we're going to evaluate that from 0 to pi over 8. And I'm going to call that I of x. So I of x from 0 to pi over 8. In other words, we're going to find an indefinite integral, we're going to find I of x, we're going to evaluate it at pi over 8, and we're going to evaluate it at 0, and we're going to subtract. So we're going to resume that here. Now off to the side, as I always did, so as I mentioned many times, I like to have a single calculation that goes from beginning to end. If I want to break something off, I put it off to the side where it doesn't interrupt that equation, that string of equations. So indefinite integral details I'm going to do over here. So I have my I of x, which is the integral of sine squared x cos squared x. Now there's more than one way to proceed here. Here's the way I decided to proceed, and it worked, so I'm going to use it. So I'm going to combine those into sine x cos x, that whole thing squared. Now look over here. There's a sine x cos x here. So if it didn't have the 2, so if I divide both sides of this by 2, I get sine x cos x would be sine 2x all divided by 2. So let's put a star by this equation. And that's what we're going to use here. We're going to replace this with 1/2 sine 2x. Now keep in mind that's all in parentheses being squared. You've got to keep track of parentheses here. Now that 1/2 can be pulled out. It comes out in front as a 1/2 squared. There we go. Now we've got a sine 2x. I'm sorry. We've got a sine 2x. We could use this again, which would do us no good because it would get us back to where we started. But sort of take off your glasses if you're wearing glasses And this is just sine of something squared. All right, well, let's look over here. Sine of something squared, we can use this formula. Let me get, sorry, Gabriel, I keep running back and forth. I'm trying to get my steps in, so I'm just going back and forth as often as I can. Let's use this to replace this whole thing. So we're going to have the integral of 1 minus cos of 2 times 2x, so that's going to be 4x. And then that's all going to be over 2. And there's still a 1/4 out front. So this is going to be 1/4 the integral of 1/2 minus cos 4x. Well, that's a dumb way to do it. Just pull out the 2 in front. So this is 1/8 the integral of 1 minus cos 4x. So 1/8 the integral of 1 minus 1/8 the integral of cos 4x. Integral of 1 is easy. An antiderivative of 1 is x. But here, we're going to need to do something here. Let's do substitution. Hey, I have orange chalk. So we're going to need to do substitution here. So off to the side, I'm not going to interrupt the flow of this. I'm going to do the substitution details over here. So we have the integral of cos 4x. So I'm going to do what I always do with substitutions. Got to have the right color chalk. Where's my green chalk? Oh well, I won't use green. We're going to find a new version of the inner function. I'd really rather not have this 4x, so I'm going to make that my u. And then I also find a new version of the dx. I always do 1 over u prime du. And so that's going to be my red substitution. Oops. So when I make those substitutions, I get integral of cos u times 1 over, oh, and this should be 1 over 4 du. So this is going to be 1/4 the integral of cos u. So that's 1/4 of sine u. Now there is a plus c here, but we're eventually going to be doing a definite integral, so I'm just going to ignore the plus c's. So all this stuff is the definite integral, the substitution details. So that all goes here. I guess this should have gone here. That's where we used it. So we end up with 1/8 x minus, oh, and I forgot to substitute back. 1/4 sine 4x. So this should be 1/4 sine 4x. So I end up with 1/8 x minus 132 sine 4x. That all goes all those indefinite integral details go here. So that's my I of x. So we need to plug pi over 8 into that. 1/8 pi over 8 minus 132 sine of 4 times pi over 8. And then that's one of my terms. And then I need to subtract 1/8 of 0 minus 1/32 of sine of 4 times 0. So this becomes pi over 64. This becomes minus 132 of sine of pi over 2. That becomes minus 0, and that becomes plus 1 over 32 sine 0. Okay, well that's 0, and that's 0. What's sine of pi over 2? Well, that's just the number 1. So I get pi over 4 minus 1 over 32. So notice in this integral, we used double angle formulas. We actually had to do 2 different double angle formulas. And we had to do substitution. Now there are some examples in the book where you do a double angle formula and then you do the trick of breaking off a sine or cosine. So there are all these different general categories. And so study the book, because the book does a really nice job of presenting them. And again, as always, quizzes and exams will include book examples. All right, so if you would please put everything away. Gabriel, we're done. Thanks for filming.